It's nice to be here in person for the first time and I think for the first time in actually my entire graduate program. So really happy to talk about this work with real people and not people over Zoom. So I think the focus of today's talk is going to be about the idea that the census has some requirements for releasing some statistics with privacy protections from a differential privacy framework, and others are based on these sort of legal and other normative constraints. And we want to think about, when we're in a situation where we have to think about these simultaneously, how does that change the quantitative way that we think about privacy, the way that we think about utility, either from a situation where we're designing a particular mechanism or, like many of us in this room are doing, are adjusting an inference given that we do not actually design that mechanism itself. So public information is something we've seen all the time. Last time when we talked about a TDA, in that we have this noisy measurement file, which contains this collection of private statistics, and we have all of these invariants and structural constraints that are representative of information that we're not releasing with any additional noise due to privacy preservation. And when we started looking at this question, we started realizing that this is not simply a problem with the census, it's a problem with all sorts of organizations that release data, especially organizations in the official statistics and in the federal statistics context. So there's lots of kinds of public information that often bypasses this sort of nice mathematical formalism that we have in differential privacy. This is true in terms of what we saw for tabular data summaries with the census, but it's also true when we think about data that has implicit constraints, such as if we're releasing a covariance matrix, we know that it lives on a particular manifold, as an example. There's also information when it comes to the way that organizations release data in time, because they're often releasing information about the same sample at different points in time, and they may choose to use a formally private method given that they've already released some information about that population. This is true when we think about temporal or spatial autocorrelation, which many demographers have talked about today. It's also true when we think about survey methodology, because plenty of survey scientists are likely to release survey information about the people who they sample without those privacy guarantees as a way of establishing the trust between a survey administrator and the people that they're trying to serve in terms of collecting that data. So it means we not only need to think about the ways in which we're normatively required to bypass sort of these differentially private effects, we need to think about what they imply for differential privacy as a whole, because all of these effects are coming from external societal forces. These are things that happen either at the time of implementation, in terms of compliance with laws, in terms of compliance with existing norms. It could also be something where there could be information released before an organization has decided to use a formally private methodology, and the relationship there becomes somewhat ambiguous because it depends on the perspective from which you define a database, the perspective from which you define adversarial information. And this is somewhat of an open question for DP, simply because DP, in order for us to maintain these strict guarantees, requires that we don't release any statistic of the confidential data as is. And when we do end up having to do this for these reasons, it becomes a little bit more challenging for us to interpret, what are the actual privacy guarantees that we have? What are the kinds of adversaries we're protecting against or not? And it points to something which has been a bit of a theme throughout this whole workshop, at least yesterday, which is that there's this growing gap between the way we think about differential privacy theoretically and these real logistical constraints that arise when we start thinking about it in situations as complex as the US Census. So what I want to talk about today is a way in which we can tweak the formalisms associated with differential privacy to accommodate this style of information in terms of what we can do to change our unit of analysis. And in doing that, we can think about both the design perspective in terms of how we might design differentially private mechanisms for releasing data, and thinking about what that means for our ability to either do inference from those results or potentially adjust results, as we saw in some of the use cases yesterday. And I'll briefly touch on two case studies specific to a couple different federal data sets and talk about what this means not only for how we think about the US Census, but also how we think about other federal statistical agencies that might want to use differential privacy or other formal privacy techniques in the future. So when we're thinking about the situation, we're in a place where we're generally interested in some parameter of interest. We have some data set that we're trying to think of X. And instead of thinking about a single statistical result that's protected by differential privacy Y, we're in the situation where this additional random variable z doesn't have the same mechanistic information applied to it. And even though we can abstract this away to think about z and y as separate entities, oftentimes we don't actually observe both z and y. Usually we observe some function of the two that makes them agree. In this case, we can think of this function as the top-down algorithm, which would be something that would post-process these results in a way that would allow us to actually ensure that y and z agree. And what we're going to talk about today is thinking more about the potential benefits of working with y and z from a technical perspective. So in order for us to do that, we need to think a little bit more holistically about the data generating process, because when we think about the kinds of dependencies induced by this public information, it's not strictly something that is deterministic. It's something where we're thinking about a property of a conditional distribution, what we could learn from this public information and how it informs what we're actually thinking about. So we're going to maintain two sort of big differences between our formalism and differential privacy. The main one being, in differential privacy, we have this idea of we can compare databases that differ on one individual entry. And we're abstracting that away with secrets, or two different events or sets that occur with different probabilities. And what we're saying is we're looking at all the secret pairs that our data that we get publicly doesn't tell us something deterministically about. So if we release some result without differential privacy guarantees, and we know that between two particular databases, we know for sure that one of them is the true one and one is the other one, we exclude that from our list. But we still maintain these relative semantics in terms of changing the amount of inference relative to a particular starting point. And what that means is when we're doing this, we are fundamentally changing the unit of analysis. So it sits somewhere in between what we might do in a traditional statistical disclosure limitation setting, where we're only really ensuring that our guarantees hold over one particular set of equivalence classes of databases, but it's not quite as strong as differential privacy because there are database pairs that we're explicitly excluding because of this public information that we've had to release. So this formalism, epsilon dp, relative to this random variable z, sits somewhere in the middle. And in doing that, there's some good things and there's some bad things about this. So the problem mainly being that because we no longer have these uniform guarantees, the kinds of theoretical reconstruction protections that we have are not necessarily going to hold for the databases that we've removed from this complete schema into this partial schema because of releasing this public information Z. At the same time, though, we can think for those databases that aren't excluded, what are the properties that we have from a privacy perspective, and how does this relate not only to the sort of methods that we have in differential privacy, but also statistical disclosure limitation methods which have existed in the official statistics context for a very long time. So the reason we're thinking about this in terms of these inferential guarantees is that it allows us, when we think about these data generating distributions, to have the same nice properties that we would have in a traditional epsilon dp setting. So these are things like robustness to post-processing. In this case, given the public information, which is not necessarily true if you only have the result without considering the effect of the public information in a traditional DP setting. We also have sequential and parallel composition and the same sort of testing-based Bayesian semantics now based on our public information Z. And what's nice is it allows us to think about a sort of new interpolation between a best case and a worst case scenario. The best case being where our public information doesn't induce any dependencies between our rows in our database, and a worst case scenario where our public information tells us everything and our privacy guarantees are pretty much trivial. And what this means is that we need to think about a new way of how statistics change as a function of changing one of these conditional distributions. And instead of being the way that we think about this in traditional mechanism design, which is, if I change one person's count, how does that change a set of marginal queries? We're now thinking about moving probability mass. And when we're thinking about moving probability mass, this turns into an optimal transport problem. So there was a little bit of preliminary work on this at Song et al. In 2017. What we did is extended it to a general class of mechanisms that are based on a new sensitivity for a generic loss function that where we first look at this place here, where we're saying what is the most probability mass that can move when we're learning the difference between one of these secrets and another of these secrets in these conditional distribution sense. And then we're looking at, given this potential distance, what is the most that a particular loss function could change given two databases that move in this worst case scenario by this information-induced Z. And what we can do is we can come up with analogs of mechanisms that are going to satisfy this relaxation of epsilon differential privacy. And there are a couple key things that I want to point out here about this analog to the exponential mechanism. One being that, so I guess I should say, first of all, for those of you not familiar with this mechanism, it's a sort of generic way of writing a particular privacy data release based on trying to solve an optimization problem based on a loss function L while satisfying some formalism such as differential privacy. Now, what makes this different from the traditional mechanism is two different things. One is that we have this new sensitivity that's induced by this public information. The other big thing is that our public information is now part of our base measure. And this is something that is going to be particularly important today because we can start to think about when we change this base measure, how we can incorporate this public information in a way that avoids a lot of the problems associated with post-processing. So instead of, say, producing a negative count and having to edit it ex post facto, this is something where we could choose a base measure, say, over all such databases that conform to non-negative counts that agree with a collection of, say, private summation queries. And this is something where the choice of this base measure could not only incorporate this congeniality with public information, but could also incorporate prior information in that it becomes a bit of a modeling problem as well in terms of the degree to which this public information might tell us something about the distribution of X, where it could be probabilistic. Say, if we know the approximate prevalence of a disease from a public pilot study, that might tell us something about whether we should be more concerned about smaller scale databases towards, in terms of like the order of magnitude of the prevalence of that disease affecting how you move your prior. And additionally, we have a corollary in our paper where we talk about a way in which if we choose this loss function as the norm of a gradient, then we can ensure that asymptotically the noise due to privacy will be negligible due to the noise due to sampling. So we have like central limit style phenomena, which is nice. So that's all from a design perspective. Now, for most of the people in this room, I guess I should say it's a mix of people in this room in terms of whether or not you think about privacy from one of two perspectives. The first perspective being the idea that we're presented with a particular problem and a particular privacy constraint, and we have the freedom to design that mechanism and the freedom to adjust, and we have the freedom to think about the associated estimator with that mechanism. However, for the noisy measurements file, for everything that we've been talking about today, we're more likely to be, in terms of the stakeholders from yesterday, in the second section, where we don't get the choice of what the mechanism is, but instead we want to adjust it for a particular inferential class. And it's true that accounting for those errors due to privacy is going to be something essential to both processes, but what's going to be different is that the way in which we define optimality for one group of problems is not going to be the same as the way we define optimality for another group of problems. And this is sort of a high-level overview of some of the results and what they imply. So at a high level, when we think about the effect of public information, a lot of the effects of public information asymptotically are not the kinds of things that necessarily show up in sample complexity arguments unless there's something that we can do to explicitly reduce the space of possible results. So there's a paper by Basili et al. That uses public information to, I believe, come up with some sort of representer class, and that allows them to do private learning on a particular query class. And that can be helpful asymptotically, but a lot of the effects that we see in terms of this congeniality are not things that we have those same effects. And this difference between how we choose a particular kind of optimality, either whether it's distance to a confidential result or different distance to an inferential procedure, is something where you're not necessarily going to have the same mechanism either case in a finite sample problem. And regardless, whenever we're in an adjustment scenario, we're going to lose information whenever we post-process. And that's something that I'd like to focus on today, is this sort of other quadrant here. And this is a problem where, I think a lot of the people in this room were we're sort of used to only working in one of these quadrants because that's sort of what our domains specify. And I think taking a step back and seeing that not all of these quadrants are going to produce the same results for the same problems is really important. So when it comes to, do we have time for, yeah. Okay. So what I'd like to focus on for the last couple of minutes of this talk is thinking about the problems associated with the difference between doing inference on Y and Z versus doing inference on this post-process result Y star. The main results being that the finite sample inference is going to be improved in expectation when we work with both the equivalent of the noisy measurements and this invariant information. And for exponential family models, we could be in a scenario where any test based on the post-process result could be uniformly improved by any test based on the combination of Y and Z together. And additionally, even when we have asymptotically optimal results in terms of how we might define a particular mechanism, there are smaller scale pieces of auxiliary information in terms of how we set up these kinds of testing problems that could potentially limit the way in which we set up these in a finite sample setting, say for toggling type 1 or type 2 error. Additionally, there's issues that we've talked about throughout the day yesterday in terms of the computational tractability of working with Y and Z, given the sort of undetermined tractability computationally of working with this post-process Y star. And we have a couple examples in our paper and some previous case study work where we derive approximate Bayesian computation algorithms for performing the sampling exactly. And as an example for why this, I'm sorry, I think we might have lost. Oh, there we go, sorry about that. So as an example of why this adjustment for uncertainty is particularly important, we're in a situation in this first case study where we're looking at rural mortality rates in rural Alaska. And what we did was we looked at public data from 2010, where we synthesized private data 2 different ways, one based on post-processing and one based on this approximate Bayesian computation procedure. And what we noticed was that we were in a situation where we had a lot better concentration around our true value, which from our data generating parameter, which is this blue line here. And when we were working with the post-process data, we were more likely to create extreme values that would cause us to underestimate the true uncertainty in our data, which is something that we were able to capture because we had exact posterior draws that captured that uncertainty due to the inference. In another setting, so it's a little bit hard to see on this projector, but what we have here is not thinking about it from the adjustment perspective, but from the design perspective, talking about how the different choices in base measure could affect the way in which we construct these different mechanisms. So what we have here are synthesis of partially private COVID-19 rates for different counties in Pennsylvania. And we see that when we are working with smaller counties, we have the ability to shrink towards our prior value, knowing that there's less signal to noise for these smaller values. So unlike the situation in post-processing where we're introducing a lot of noise and we don't know its form, this is a situation where we know what the noise is because we're shrinking towards a prior. And this naturally induces a kind of bias variance trade-off between the way in which we think about what sort of modeling assumptions we should make and how to design a good base measure given this public information. And I think that's something that would be an interesting follow-up for the people in this group. So just in order to quickly summarize, so we've introduced this sort of relaxation of differential privacy that focuses on this partially private data case, which is really important for the federal statistics context. We've looked at a couple different release mechanisms that can adjust sensitivity and secret pairs in order to think about how we might satisfy this framework. We also are in a situation where we talked about the way in which adjusting these inferences using Z conditionally instead of based on post-processing can yield both analytical and computational improvements. And there's a lot of different methods and follow-up work that could be done here from a technical perspective. There's an interesting bias variance trade-off induced by the modeling that comes from our choice of base measure. There's interesting ways of doing finite sample analysis. Yesterday we saw a lot of sort of comparisons of like top-down versus bottom-up approaches. And this might be a way of thinking about it as a sequential set of conditions that would allow us to maybe compare these a little more holistically. There's also things we can do to extend these not only to epsilon DP style semantics, but also, say, relaxations such as F differential privacy or anything that allows for more flexibility in the sort of testing interpretation of privacy. And like with any situation where we're thinking about these models, we have to think about the way in which we're specifying this public information Z, because there's some sort of fundamental normative trade-offs that we need to make here. Because it's not just a question of whether or not we need to think about how we're choosing a particular model for that public information, because we can't be either too relaxed or too strict about it, because this will run us into like the no free lunch problem, where we can't over-specify this dependence or under-specify this dependence. But resolving what that question is and what kinds of information should be part of the Z is something that we can't answer alone as technical folks, because it intersects with so many of the things that we talked about yesterday. It intersects with the way we think about, what places in existing, societal forces are the things that we need to care about when it comes to releasing this public information. It's about the way that we can make this distribution more transparent and more tractable, but it doesn't change the way necessarily that stakeholders might talk to their constituents about this. It also changes the way that we think about reproducibility for statistical results in terms of the kinds of ways in which institutions are perceived, which is something we talked about briefly, not briefly throughout the day yesterday, and also what this means for the way that which we explain privacy to a non-technical audience, because it's something that obviously does complicate things. But these are the questions I hope that we'll be able to discuss today and throughout the technical session. So that is all I had for today. Here are the papers that I talked about. Here are the emails, and here's my email, and I'm happy to take any questions. I think Adam had a question, so.
Right. Yeah. Thank you, Jeremy. So Adam will ask a question.
Sure. You actually answered one of my questions already, but I'll ask my other one, which was so the definitional structure. You're looking at, you condition X on Z and some other event, S1, some other pair of
Yes.
events. Yeah, and then so is there any constraint here on the distribution of X, or that's assumed known, or what?
So the distributions on X are coming from the version of pufferfish which instantiates the same semantics as differential privacy. So you allow for arbitrary distributions in every individual database entry, but they must be independent of each other. So this is how
even conditioned on Z, or
so when
no.
you condition on Z, then you induce the dependence. So the specification problem comes from how you specify this class of conditional distributions.
Okay.
So an example might be, maybe you release like some sort of summary statistic about, say, the number of people in a couple different partitions of your database. So the number of people in, say, race or ethnic categories. If you assume that within those race and ethnic categories, there's no other information that you get from Z, that they're still mutually independent within that, then you would have the same style of semantics as traditional differential privacy. The problem is a lot of the cases that we've talked about, that's not necessarily true. So like an example could be Joe Salvo from New York City, City of Public Planning, had an example where he was looking at housing quarters for, I believe it was, I want to say Brooklyn or the Bronx or one of the big boroughs, and he noticed that you could impute similar results just by looking at spatial autocorrelation of missing districts based on sort of like his knowledge of that system. So this is why it's not strictly a technical question, but a normative question of how do we choose the Z, because part of it we want to be respectful for the original idea of DP, which is we don't want to, say, protect against population level inferences, because we know that from the traditional work of Delaunius, that's not going to be feasible. But at the same time, oftentimes these organizations have created the data that informs these potential adversaries. So it's a weird trade-off.
But like in the definition, you're assuming somehow that the X is, there's no quantifier over X here, over the distribution over X. So that's like fixed as part of the definition.
Yes, but the part of the definition that matters is the way in which you specify the conditional distributions, because the marginal distributions on X are given from pufferfish.
I see. So you're saying you specify these conditional distributions and marginal is implied.
Yes.
Okay.